Everything dies. You, Mr. The stars in the sky. Even black holes, given enough time, will eventually evaporate into nothing. But what about atoms? The smallest, most fundamental building blocks of reality. Do they live forever? Or is there a final, inevitable fate waiting for every last atom in the universe? Right now, you're surrounded by atoms that have existed since the beginning of time. The atoms in your body, in the air you breathe, in the chair you're sitting on. Some of them were once forged in the heart of stars billions of years ago. And yet, despite their incredible longevity, atoms do not last forever. One day they will decay, they will fade, they will vanish. This is the story of the death of atoms. It is not just the end of matter, it is the final chapter of existence itself. Atoms are often seen as immortal. After all, they survive beyond human lifetimes, beyond planetary destruction, beyond the death of stars. They are the oldest relics of the universe, existing since the dawn of time. But atoms are not eternal. Every process in the universe, from the birth of stars to the decay of black holes, follows an inescapable rule. Nothing lasts forever. For centuries, scientists have studied how matter behaves, and for a long time, it seemed like atoms were stable. They don't rot like fruit, or wither like plants, or break apart like planets colliding. They persist, but only for now, because something lurks beneath their surface, an unavoidable fate. One day, even the most stable atoms in the universe will begin to disintegrate, and when they do, the fundamental structure of existence will collapse. We are used to the idea of lifespans. A human might live for 80 years, a tree for 500 years, a mountain for millions of years. Stars can burn for billions of years, shining long before Earth was born and long after it is gone. But atoms, they seem to defy time itself. The hydrogen atoms inside you, some of them were created just a few minutes after the Big Bang. They've never broken down, never faded, never changed in nearly 14 billion years. How is that possible? To answer that, we need to understand the nature of atomic stability. Atoms are held together by forces stronger than anything else in the universe. The strong nuclear force, the most powerful of nature's four fundamental forces, binds protons and neutrons together in a nucleus so tightly that not even the explosion of a supernova can tear them apart. This is why atoms survive the deaths of stars. They are resilient, able to endure the most violent cosmic events, but not indefinitely. Because deep inside, even the most stable atom carries a hidden expiration date. Atoms, despite their legendary durability, are not invincible. Some atoms are already dying. Radioactive elements like uranium and thorium slowly break down over time, decaying into lighter elements through a process called radioactive decay. These atoms have a half-life, a ticking clock that determines when half of a given sample will have transformed into something else. For example, uranium-238 has a half-life of 4.5 billion years. That means half of any given amount of uranium-238 will no longer be uranium after that time. This process is happening right now, all around us. Every radioactive atom in existence is slowly breaking down, piece by piece. But what about stable atoms, the ones that don't seem to decay? This is where the most terrifying revelation in physics comes in. Because even the most stable atoms in the universe are not truly immortal. Physicists predict that protons, one of the fundamental building blocks of atoms, may not last forever. If proton decay is real, then every atom in existence carries a hidden doomsday clock. It may be ticking so slowly that it takes trillions upon trillions of years to reach zero, but once it does, every last atom in the universe will dissolve. This is not just the death of matter, it is the death of existence itself. At this moment, the universe is still young. Atoms are everywhere. They make up stars, planets, and life itself, but their fate is sealed. One day, in the distant future, the last atoms will begin to break apart. When that happens, what will be left? Will the universe be a frozen wasteland of scattered subatomic particles? Or will something new emerge from the ashes of dying atoms? This is the story of the final fate of all matter. When the last atoms fade away, will anything remain? And more importantly, what does this mean for us? Atoms are the foundation of everything we know, our bodies, our world, the stars, and even the vast, seemingly endless fabric of the universe. They have existed for billions of years, shaped by forces beyond comprehension, forming and reforming through cosmic cycles of destruction and creation. But where did they come from? If atoms are not eternal, then when did they begin? To understand their fate, we must first understand their origins. Over 13.8 billion years ago, the universe as we know it was born in an event known as the Big Bang. This wasn't an explosion in space. It was an explosion of space itself, an unimaginable expansion that took the universe from an infinitely small singularity to an ever-growing cosmos. For the first few moments, the universe was a seething cauldron of pure energy, a place where atoms as we know them could not yet exist. In the first trillionth of a second, temperatures were so high that even the fundamental building blocks of matter, quarks and gluons, could not bind together. The universe was pure chaos, a cosmic inferno where everything existed as free-floating energy. But as the universe expanded, it began to cool, and as it cooled, energy condensed into matter, following one of the most fundamental laws of physics, Einstein's famous equation E equals mc squared. Energy and mass are two sides of the same coin. At around 1 microsecond after the Big Bang, the first protons and neutrons formed. These were the earliest building blocks of what would eventually become atoms. But there was a problem. The universe was still far too hot and dense for these particles to stabilize into atoms. Instead, they existed in a dense plasma-like state, colliding and smashing into each other at near-light speeds. It wasn't until about 3 minutes after the Big Bang that things began to settle. This was when nucleosynthesis occurred, the process where protons and neutrons fused together to form the first atomic nuclei. Hydrogen, the simplest and most abundant element in the universe, was the first to form. Just a single proton, hydrogen, is the backbone of all matter. But in some cases, these protons combined with neutrons to create helium, a heavier element that would later play a crucial role in the formation of stars. A tiny fraction of lithium also formed in this early stage. But the universe was still missing something. At this stage, these were not yet atoms. They were just atomic nuclei. They lacked a fundamental component: electrons. For the next 380,000 years, these atomic nuclei existed in a dense fog of charged particles. The universe was still far too hot for electrons to attach to these nuclei. Every time they tried, they would be ripped away by the intense radiation left over from the Big Bang. Then something extraordinary happened. About 380,000 years after the Big Bang, the universe finally cooled enough for electrons to bind to nuclei, forming the first true atoms. This period is known as recombination, and it was one of the most transformative moments in cosmic history. The universe transitioned from an opaque, chaotic plasma to a transparent, structured cosmos where light could finally travel freely. The first photons, no longer constantly colliding with free electrons, could now move unimpeded through space, creating what we see today as the cosmic microwave background radiation, the faint afterglow of the Big Bang. For the first time, atoms existed. But these were simple atoms, hydrogen and helium, with just a trace amount of lithium. These elements were the only ingredients available in the early universe. Heavier elements, everything from carbon to iron to gold, did not yet exist. The universe was a vast sea of hydrogen and helium gas stretching into infinity. And for hundreds of millions of years, that was all there was. Without heavier elements, there were no planets, no complex molecules, no life. The universe was waiting for something. And then, the first stars were born. Over time, gravity pulled these clouds of hydrogen and helium together, compressing them until they became so dense that nuclear fusion ignited in their cores. These first stars were unlike anything that exists today. They were monstrous, hundreds of times the mass of our Sun, burning hotter and faster than any modern star. Inside these fiery infernos, something remarkable happened. Nuclear fusion began to forge heavier elements: carbon, oxygen, nitrogen, silicon, and eventually iron. The first generation of stars became cosmic factories, churning out the elements that would one day make up planets, oceans, and life itself. But atoms do not last forever, not even the ones inside stars. Massive stars live fast and die young. Within just a few million years, they reach the end of their fuel supply and explode in some of the most violent events in the universe: supernovae. Supernovae do more than just destroy stars. They scatter heavy elements into space, enriching the universe with carbon, oxygen, iron, and even gold. These atoms, once locked inside stellar cores, are now free to drift through space, waiting to become part of something new. Over billions of years, these atoms recycled through multiple generations of stars, forming planets, moons, and eventually life itself. Every atom in your body was once part of a star. But even though stars can recycle atoms, atoms themselves are not immortal. They are formed, transformed, and eventually they will decay. Some atoms, like hydrogen, have persisted since the Big Bang. Others, like carbon and oxygen, have existed for billions of years inside stars and planets. But every atom carries a hidden expiration date, one that may spell the end of all matter as we know it. The universe has been recycling atoms for billions of years, but one day, that process will stop. And when it does, what happens next? That is where the true story of atomic death begins. Atoms are the foundation of everything we see, everything we touch, and everything we are. They have shaped the universe from its infancy, built the stars, carved out planets, and provided the very chemistry that makes life possible. But they are not eternal. Even the strongest forces in the universe have limits. Atoms, for all their resilience, are no exception. For most of cosmic history, atoms have been trapped in an endless cycle of destruction and rebirth. They have been forged in the heart of stars, torn apart in supernova explosions, and scattered across the galaxy to become something new. The atoms in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood, each one has traveled an unfathomable journey through deep time. But there will come a point where this cycle ends. Atoms will no longer be recycled. Matter will no longer transform. One day, all change will cease. The reason is simple. Energy drives the universe, and energy is finite. Every process, every reaction, every transformation of matter relies on energy. But as time moves forward, energy becomes harder to use. Stars consume fuel, galaxies drift apart, and black holes swallow whatever they can. This is the slow unraveling of the universe. And at the very core of it all, atoms will be the last to fall. For now, atoms still serve as the foundation of existence, but they are not indestructible. There are forces in the universe capable of breaking them apart. Nuclear reactions, cosmic radiation, and extreme gravitational forces can tear atoms to pieces. In some cases, atoms do not decay naturally, but they can be destroyed through violent interactions with their surroundings. Some of these processes are already happening, shaping the universe in ways we cannot see. Others are still far in the future, waiting for the day when atoms meet their final reckoning. Deep in the cosmos, atoms are already dying. High-energy cosmic rays, subatomic particles traveling near the speed of light, bombard atoms across the universe, shattering them into smaller components. Every second, trillions of cosmic rays pass through the Earth, some powerful enough to break apart atomic structures. These collisions create showers of secondary particles, like muons and neutrinos, which pass through matter undetected, continuing their journey across the universe. Atoms, seemingly stable and unbreakable, are constantly under attack by forces beyond our perception. But cosmic rays are just one of many threats. Neutron stars, the collapsed remnants of massive stars, generate some of the most extreme environments in the universe. Their gravity is so intense that atoms at their surface are crushed beyond recognition, their electrons forced into their protons, turning everything into a sea of neutrons. This is what happens when atoms meet forces too powerful to resist. The very structure that defines them is stripped away, leaving behind something more fundamental. The idea that atoms can be deconstructed, reduced to their basic parts, is a reminder that their existence is not permanent. And then there are black holes, the ultimate destroyers. If an atom falls into a black hole, what happens? Does it get crushed into oblivion, or does it still exist in some form? The truth is, no one knows for certain. Some theories suggest that matter inside a black hole is compacted into an infinitely dense point known as a singularity. Others propose that atoms may never truly be destroyed, but instead become part of the black hole itself, contributing to its mass and energy. But the most unsettling possibility is that information about those atoms is permanently erased. If that is the case, then black holes represent something truly final, the complete loss of matter, with no hope of recovery. Yet for all these destructive forces, atoms endure. Some atoms have survived for billions of years without breaking down. Even in the most extreme conditions, there are elements that persist, defying entropy for now. But no matter how long they last, even the most stable atoms are not immune to time itself. Because hidden deep within the laws of physics is an unsettling truth. Everything, given enough time, must decay. The idea that atoms will one day decay is not just speculation. It is one of the most profound implications of modern physics. Protons, the very foundation of atomic structure, are believed to have a finite lifespan. It is not something we can observe directly, because the predicted lifespan of a proton is staggeringly long, trillions of times the current age of the universe. But if protons do decay, then that means every atom in existence carries a countdown clock, one that is imperceptibly slow but inevitable. This raises an extraordinary question. If protons decay, what happens to matter itself? If all atoms slowly disintegrate over unimaginable timescales, does that mean everything will eventually dissolve into nothingness? The answer to this question holds the key to the fate of the universe. Scientists believe that in an unimaginably distant future, the universe will reach a state known as heat death, a time when all usable energy has been spent, when stars no longer shine and black holes no longer consume. When this happens, only the atoms will remain, floating in a cold, empty void. But if protons decay, even the atoms will not last. Over time, they will break down into subatomic particles, which will themselves fade into background radiation. The final stage of the universe may not be an explosion, nor a collapse, but a slow fading into darkness as the last remaining matter disintegrates into nothing. This is not just a theory. It is a prediction based on everything we know about physics. If it holds true, it means that all matter, all structure, all existence will eventually be erased. Nothing will remain. No atoms, no particles, no motion. Just a dark, empty universe with nothing left to change. But could there be another way? Could atoms escape this fate? Could something unexpected emerge from the ashes of a dying universe? These are the questions that physicists are still trying to answer. Some propose that quantum fluctuations, random bursts of energy in empty space, could one day create new particles, even new atoms. Others suggest that the universe itself might not be truly dead, but could cycle through a new Big Bang, giving birth to atoms once again. For now, atoms still exist. They make up everything we know, and they will for trillions of years to come. But they are not eternal. Their destruction may be so far into the future that it seems irrelevant to us now. But in the grand scale of time, the death of atoms is an inevitability. And when the last one finally fades, the universe as we know it will be gone forever. Atoms have shaped the cosmos for billions of years, but their existence is not permanent. The forces that hold them together, the delicate balance of energy and fundamental interactions that give them form, are not immune to time. In the far reaches of the universe, atoms are already meeting their end. Some are torn apart in violent cataclysms, while others slowly decay over unimaginable timescales. But what actually happens when an atom dies? What does that process look like on the smallest scale, and what does it mean for the fate of all matter? At the most basic level, an atom is a system of charged particles held together by fundamental forces. The nucleus, composed of protons and neutrons, sits at the heart of the atom, bound together by the strong nuclear force. Surrounding it are electrons, orbiting in probabilistic clouds rather than defined paths. This structure makes atoms incredibly stable, resistant to most external forces. But stability does not mean permanence. The most well-known form of atomic decay is radioactive decay. This is a natural process in which an unstable atomic nucleus loses energy by emitting radiation. There are several types of radioactive decay, each with unique effects on the atom. Alpha decay occurs when an atom ejects a helium nucleus, 2 protons and 2 neutrons, reducing its atomic number and transforming into a different element. This process occurs in heavy elements like uranium and radium, slowly breaking them down over time. Alpha decay is relatively slow, taking thousands or even millions of years to significantly affect a material. Beta decay is a more complex process in which a neutron inside the nucleus transforms into a proton while emitting an electron and an antineutrino. This allows an atom to change into a new element, shifting its place on the periodic table. Beta decay is responsible for the transformation of elements in nuclear reactions and is a key process in the formation of stable matter. Gamma decay involves the emission of high-energy photons, allowing an excited atom to release excess energy without changing its elemental identity. This is the process that makes certain radioactive materials dangerous, as gamma radiation is highly penetrating and can damage living cells. While these types of decay play a role in shaping matter on Earth, they are only part of the story. Many elements are stable on human timescales, their atomic structures unchanged for billions of years. But deep within each nucleus, something is happening that could change everything. Physicists have long suspected that protons, the building blocks of atomic nuclei, may not be truly stable. The theory of proton decay suggests that, given enough time, protons can spontaneously transform into lighter particles, effectively dismantling the atom from within. Proton decay is not something we can observe easily. If it happens, it occurs on timescales vastly longer than the current age of the universe. The most advanced experiments ever conducted, including massive underground detectors, have searched for evidence of a decaying proton. So far, none have been found. But if the theory is correct, then every atom is doomed to fall apart. If proton decay is real, then the lifetime of the universe itself is measured not in billions of years, but in hundreds of trillions of trillions of trillions of years. A span so vast that even the deaths of stars, the merging of galaxies, and the evaporation of black holes will seem like fleeting moments in comparison. Imagine a universe where no new atoms form, no more nuclear fusion, no more element creation, no more recycling of matter. As protons decay, atoms will vanish. Over incomprehensible spans of time, entire galaxies will dissolve, leaving behind a void scattered with subatomic remnants. And then there is the question of what remains. When an atom breaks apart, its components, quarks, electrons, neutrinos, are not destroyed, but they may lose the ability to form structures, A proton decaying into energy does not cease to exist, but it becomes part of the background radiation of the universe, an energy signature left behind by a once solid form of matter. Some theories suggest that in the final moments, when atoms are no more, the universe may transition into something new. Quantum mechanics suggests that fluctuations in empty space can create brief bursts of energy. Could these fluctuations eventually seed a new reality, a new cycle of formation? Or will the end of atoms mark the ultimate stillness, the true end of all things? For now, atoms are still here. They bind the universe together, forming everything from the simplest molecules to the most complex life forms. But the forces that sustain them will not last forever. As the universe ages, atoms will succumb to the same fate as everything else. One by one, they will disappear. And when the last atom is gone, the universe will enter its final, most unknowable chapter. The universe has always been in motion. From the first chaotic moments of the Big Bang to the formation of galaxies, stars, and planets, matter has been caught in a continuous cycle of transformation. Atoms, the smallest units of this grand structure, have persisted through it all. But what happens when that cycle ends? What does a universe without atoms look like? To understand this, we have to follow the timeline of the far future, beyond the death of stars, beyond the last black hole, to a time when the fundamental building blocks of matter themselves begin to fail. In the present universe, atoms are still thriving. Stars are burning hydrogen into helium, creating heavier elements in their cores. These atoms are spread through space when stars explode, forming new planets, new molecules, and new structures. This process has been ongoing for billions of years, continuously recycling atoms from one form to another. But this cosmic cycle is not infinite. The first major change will happen when star formation ceases. Right now, new stars are being born in galaxies across the cosmos. But as time stretches forward, the raw materials needed to form new stars will be used up. The brightest, most massive stars will burn through their fuel quickly and explode, while smaller stars like our Sun will slowly fade into white dwarfs, cooling over trillions of years. At some point, the last star will flicker out. Without stars, there will be no more fusion, no more light, no more new elements being forged. The universe will become a place of cold, dark remnants, white dwarfs, neutron stars, and black holes drifting endlessly through an expanding void. During this phase, atoms will still exist. They will make up the lifeless remains of once thriving galaxies, locked in the frozen husks of planets and stellar corpses. But without energy to sustain complex processes, these atoms will exist in a state of stagnation. The next phase will be dictated by black holes, the last major forces in the universe. Over time, they will consume whatever remains: gas clouds, dead stars, even other black holes. But even black holes are not eternal. Through a process known as Hawking radiation, they will slowly evaporate, losing mass particle by particle. Given enough time, every black hole in existence will vanish, releasing its remaining energy into space as the last flickering glow of the cosmos. At this point, we enter what physicists call the degenerate era, a time when only the most basic forms of matter remain. Without stars, without black holes, only isolated atoms, frozen planets, and the occasional subatomic particle will drift through an increasingly empty cosmos. Galaxies will no longer be recognizable. The universe will be a place of extreme stillness, with nothing left to drive change. But even this state will not last. If proton decay is real, then even these scattered atoms will not remain forever. One by one, their protons will break down, transforming into lighter particles and releasing small amounts of radiation. The atoms that make up everything today, from the iron in the Earth's core to the hydrogen in distant nebulae, will slowly dissolve, fading into the fabric of space. The timeline for this decay is almost incomprehensible. If current estimates hold, the last proton might not decay for 10 to the 34th to 10 to the 40th years, a number so large that it stretches beyond human understanding. But even though it is an eternity compared to the current age of the universe, it is still a finite number. Given enough time, it will happen. As protons disappear, atoms will no longer exist. The universe will no longer be made of matter. Instead, it will be a sea of fundamental particles, electrons, neutrinos, and radiation, drifting through the void. With no new processes occurring, with no structures left to decay, the universe will settle into its final state. This is the phase known as the heat death of the universe. With no energy differentials, no usable heat, and no physical structures remaining, the cosmos will reach a state of absolute thermodynamic equilibrium. Time itself will have no meaning, because nothing will ever change again. It will be a universe of cold, quiet nothingness. And yet, even this may not be the final answer. Some physicists believe that the vacuum of space itself may not be truly stable. In quantum mechanics, empty space is not actually empty. It is a frothing sea of virtual particles, constantly appearing and disappearing. Over vast timescales, some theories suggest that a quantum fluctuation could trigger an entirely new universe, a new Big Bang, born from the remnants of the old. This be the next cycle? Could atoms be born again in some distant, unknowable future? For now, all we know is that atoms have shaped everything we see, and their fate is bound to the fate of the universe itself. They have been our building blocks, the silent witnesses to the story of existence. But they are not eternal. One day the last atom will break apart, and when it does, the universe as we know it will be gone forever. The death of atoms is not just an ending, it is a transformation on the grandest scale. Everything that has ever existed, every planet, every star, every galaxy, has been made from these tiny building blocks. Their disappearance marks the final chapter of the universe as we understand it. But is this truly the end? Or could something beyond atoms emerge from the ashes of a dying cosmos? To answer this, we must consider the farthest reaches of theoretical physics. The destruction of atoms does not mean the destruction of energy. According to the laws of thermodynamics, energy cannot be created or destroyed, it only changes form. So, if the last atoms decay, where does their energy go? As protons break down, their remnants will spread throughout space as radiation. Over trillions of years, this radiation will stretch into ever longer wavelengths, becoming colder, weaker, and more diffuse. Eventually, it will merge with the background glow of the cosmos, blending into the fabric of space itself. The universe will no longer be a place of light and structure, but a vast ocean of low-energy particles drifting in endless silence. But there is another possibility. Some theories suggest that even in this final state, quantum mechanics may hold the key to a new beginning. The vacuum of space, even at absolute zero, is never truly empty. Tiny fluctuations of energy, known as vacuum fluctuations, still occur at the quantum level. These fluctuations are responsible for the spontaneous appearance and disappearance of virtual particles, particles that exist for only the briefest fraction of a second before vanishing again. Could one of these fluctuations, given infinite time, trigger something greater? Some physicists believe that in the distant future, an extreme quantum event could generate a new universe. A fluctuation of space-time itself, if powerful enough, might create a bubble of energy that expands, inflating into a new cosmos. This process, sometimes called quantum tunneling, suggests that even in the most desolate, lifeless universe, something new could still emerge. If this is true, then the story of atoms is not one of finality, but of renewal. The atoms we know may fade, but their energy could seed a new reality, one where entirely different physical laws govern a new form of matter. Alternatively, some theories suggest that the universe itself may undergo a rebirth through cyclical cosmology. Instead of fading into a static void, the universe may eventually collapse and rebound in a new Big Bang. In this scenario, matter and energy are not truly lost, but recycled in an endless cycle of death and rebirth. Atoms may not be immortal, but something like them could always return. Still, there is no certainty in these ideas. They remain speculative, untested, and beyond the reach of current physics. If the universe does not cycle, and if quantum fluctuations never trigger a new event, then the true end remains unavoidable. In that case, we are left with a universe where time itself has no meaning. A place where no events occur, no matter exists, and no future unfolds. The cosmos will not explode, will not collapse, will not burn. It will simply persist, cold and motionless, forever. For now, this remains a distant future, trillions upon trillions of years away. Atoms are still here, forming the structures we know, enabling life to exist. They will endure for longer than we can imagine. But one day, their time will come. And when the last atom fades, the universe will enter an era unlike anything before it. One of absolute stillness, or perhaps one of unimaginable new beginnings. As the final atoms decay and the universe drifts toward its ultimate fate, a haunting question lingers. Was this always inevitable? Is the death of all matter an unavoidable consequence of time itself? Or is there some unknown mechanism that could disrupt this fate? To understand this, we need to consider the fundamental forces that govern the behavior of atoms, the same forces that, given enough time, will dictate their end. There are four fundamental forces in the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these has played a role in shaping matter, but in the final era of the universe, they will determine how, and if, matter survives at all. The strong nuclear force is what holds atomic nuclei together. It binds protons and neutrons, preventing them from flying apart under the repelling force of their positive charges. This is the force that allows atoms to exist in the first place. However, if protons are not truly stable, if they are doomed to decay over vast timescales, then the strong force will eventually be rendered meaningless. The weak nuclear force governs radioactive decay. It allows particles to change their identities. Neutrons can turn into protons, or vice versa, in certain conditions. This force is responsible for the slow transformation of elements over billions of years. But in the far future, when all complex interactions have ceased, it too will play a role in the disintegration of atoms. Electromagnetism is what keeps electrons bound to atomic nuclei. It is the reason atoms form chemical bonds, the reason molecules exist, the reason light interacts with matter. But when the last stars fade and energy levels become too low to sustain interactions, electromagnetism will cease to have any effect on large scales. The universe will no longer be a place of chemistry or reaction. It will be a place of isolation. And then there is gravity. Gravity has shaped the universe more than any other force, pulling matter into galaxies, driving the formation of stars, and fueling the engines of cosmic evolution. But in the long run, gravity is not strong enough to prevent the unraveling of matter. As space continues to expand, gravity will weaken on cosmic scales, allowing everything to drift apart. If protons decay, then even the gravitational pull of collapsed objects like neutron stars will become meaningless, because there will be nothing left to attract. This means that the final state of the universe is determined by forces that, for billions of years, have shaped everything we know. The same interactions that once allowed atoms to form, to bond, to create planets and life, will eventually unravel all of existence. But could there be unknown forces at play? Could something intervene in this slow march toward oblivion? One of the biggest unanswered questions in physics is the nature of dark matter and dark energy. Together, these unseen forces make up 95% of the universe, yet we know almost nothing about them. If dark matter interacts with atoms in ways we do not yet understand, It could influence their fate in ways we cannot predict. Similarly, dark energy, the mysterious force that is accelerating the expansion of the universe, could one day change its behavior. If dark energy increases in strength, it could trigger a big rip, tearing apart atoms long before proton decay ever becomes relevant. If it weakens, the universe might instead contract, leading to a new phase of existence. These unknowns leave a sliver of possibility that the story of atoms is not yet fully written. Some speculative theories suggest that new physics may emerge as the universe ages. If the vacuum of space itself is unstable, a quantum fluctuation could reset the fundamental laws of reality. In this scenario, what we call atoms today may not even be recognizable in the far future. New forms of matter, governed by entirely different rules, could arise from the ashes of the old universe. For now, however, all available evidence suggests that atoms, as we know them, are not eternal. Their time is measured in trillions of years, but their fate is inescapable. We exist in the brief window of cosmic history where atoms still thrive. They have built galaxies, worlds, and life itself. But in the end, they too will fall victim to the relentless passage of time. And when the last one fades, the universe will either enter its final, silent state or be reborn into something entirely new. As we stand at the precipice of theoretical time, contemplating the end of atoms, a profound realization takes hold. This story is not just about physics. It is about existence itself. Atoms are the foundation of everything we have ever known, yet their eventual demise forces us to question the permanence of reality. If the very building blocks of the universe are not eternal, then what does that say about our place in the grand scheme of things? The death of atoms is not merely an event that will unfold over incomprehensible timescales. It is the ultimate expression of entropy, the gradual decline of order into disorder. It is a reminder that everything, no matter how fundamental, has a finite lifespan. This idea is unsettling, but it also raises deeper questions about the nature of time, change, and the possibility of something beyond the physical. Some scientists argue that time itself may be an illusion, a byproduct of the way we perceive change. If atoms fade, does time cease to exist, or does it simply become meaningless in the absence of matter? The universe in its final state will no longer have motion, heat, or energy gradients, things that define our understanding of time. If nothing moves, if nothing changes, then does time itself still flow? This leads to a concept known as the timeless universe, where after the death of atoms, the cosmos enters a state where time is no longer a measurable property. In such a state, there would be no past, present, or future, only an infinite, motionless void. But what if time does not end with atoms? Quantum mechanics introduces a strange possibility. Fluctuations in the vacuum of space may still occur, even in a universe where atoms no longer exist. At the quantum level, space itself is not empty. It seethes with virtual particles that appear and disappear, borrowing energy from nothingness. Could these fluctuations eventually lead to something new? Some theories suggest that quantum fluctuations, over unimaginable timescales, could eventually give rise to new matter, perhaps even new atoms. This idea, known as quantum resurrection, suggests that the universe, even in its most lifeless state, still retains the potential for rebirth. Even more fascinating is the idea that, at the deepest level, information itself may never be lost. Some physicists argue that the fundamental structure of the universe is not based on matter, but on information, the underlying mathematical rules that govern reality. If this is true, then even if atoms fade, the pattern of existence may persist in some form, waiting for the conditions to change so that new matter can emerge. This concept aligns with the idea of the holographic principle, which suggests that all the information about the universe is encoded on a two-dimensional surface, much like a hologram. If this theory is correct, then even after the last atom vanishes, The universe may still retain its fundamental blueprint, waiting for something, some new force, some unknown mechanism, to bring it back into a new phase of existence. Alternatively, if the cyclic universe theory holds true, then atoms are not truly dying. They are simply being reset for a new beginning. In this model, the universe undergoes infinite cycles of expansion and contraction, each leading to a new Big Bang. If this is correct, then the death of atoms in one era is merely the first step toward their reformation in another. But what if none of these possibilities come to pass? What if the last atom decays and no new universe emerges? Then we are left with a truly final state, one where existence itself fades into absolute nothingness. A universe where atoms, once the foundation of everything, are reduced to a distant memory. A cosmos where even memory itself no longer holds meaning. In this scenario, there are no observers, no records, no echoes of what once was. And yet, the mere fact that we, in this moment, can contemplate this future, can ponder the fate of atoms and the ultimate destiny of all things, suggests that existence, fleeting as it may be, is something truly extraordinary. Atoms will die. That much is certain. But for now, they are here. They make up the world around us, the stars above, the air we breathe, and the thoughts we think. And for as long as they remain, so too does the mystery of what comes next. Atoms, despite their fundamental role in the structure of the universe, are not as stable as they appear. While we tend to think of them as unchanging, eternal building blocks, the reality is far more complex. Quantum mechanics, the branch of physics governing the behavior of the smallest particles, tells us that nothing is truly permanent. Not even the very atoms that make up reality itself. But what does this mean for their ultimate fate? Will atoms simply decay and vanish, or does quantum mechanics introduce bizarre, counterintuitive ways for them to persist, even beyond what classical physics predicts? To understand the full picture, we need to delve into the strange world of quantum uncertainty, virtual particles, and quantum tunneling, phenomena that could influence how and when atoms meet their end. At the quantum level, the universe is not as rigid as it seems on human scales. Particles do not behave like tiny billiard balls with defined positions and velocities. Instead, they exist in a state of uncertainty, governed by probability rather than fixed, deterministic rules. This is described mathematically by the Heisenberg uncertainty principle, which states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This uncertainty plays a crucial role in atomic stability. The electrons that orbit atomic nuclei do not follow neat circular paths like planets around the sun. Instead, they exist in a cloud of probability, constantly flickering in and out of precise locations. This bizarre quantum nature actually prevents electrons from spiraling into the nucleus and collapsing the atom. Without quantum uncertainty, atoms wouldn't even exist in the first place. But what happens when quantum mechanics, the very thing that allows atoms to persist, also sets the stage for their eventual decay? One of the strangest aspects of quantum mechanics is that particles can spontaneously appear and disappear, seemingly violating the rules of classical conservation. These are known as virtual particles, and they exist everywhere, even in empty space. Virtual particles are temporary, fleeting particles that pop into existence due to quantum fluctuations. They exist for only the briefest moment before vanishing again, and under normal circumstances, they do not significantly affect large, stable objects like atoms. However, as the universe evolves and approaches its end state, the environment in which atoms exist changes dramatically. In a universe dominated by Hawking radiation, extreme entropy and decaying matter, virtual particles could play a more active role in destabilizing atomic structures. This is especially important when considering proton decay, the theoretical process by which protons, one of the essential building blocks of all atoms, spontaneously disintegrate into lighter subatomic particles. If protons do decay, it will not be because of classical physics, but because of quantum fluctuations on an unimaginable timescale. These fluctuations introduce the possibility that, given enough time, even stable particles will randomly transform into something else. In the distant future, could virtual particles trigger premature atomic decay? Some speculative theories suggest that, in a high-entropy universe filled with low-energy radiation, the constant interaction of virtual particles with atomic structures could influence their longevity. While this is still a matter of deep theoretical investigation, one thing is certain. The longer an atom exists, the more likely it is to be affected by quantum fluctuations. Another key feature of quantum mechanics is quantum tunneling, a process where particles can seemingly break through barriers that, according to classical physics, should be impossible to cross. For example, in nuclear fusion, atomic nuclei fuse together despite being separated by strong electrostatic repulsion. This happens because of quantum tunneling, allowing particles to tunnel through the energy barrier. But could tunneling work in reverse? If protons are destined to decay over vast timescales, could quantum tunneling allow some atoms to escape this fate by shifting into another quantum state? In theory, certain atomic structures could tunnel into a different configuration that extends their existence. Some physicists speculate that under the right conditions, matter could transition into a stable, low-energy quantum state that does not decay in the conventional sense. This question leads to one of the most profound mysteries in physics. Are atoms truly doomed, or are there ways they could persist forever? Most models suggest that all atomic structures will eventually break down, but the Bose-Einstein condensate, BEC, state introduces an intriguing possibility. In this state, which occurs at temperatures near absolute zero, individual particles lose their separate identities and behave as a single quantum entity. Some physicists theorize that if an extremely cold and low-energy environment exists in the distant future, atoms might not behave as distinct structures, but instead enter a quantum superfluid state that defies conventional decay. Could a vast portion of the universe, long after atoms have seemingly decayed, still exist in this exotic quantum state? And if so, would it mean that atoms, at least in some form, never truly die? Quantum mechanics does not just describe how atoms behave today, it governs their ultimate fate. The forces of quantum uncertainty, virtual particle interactions, and quantum tunneling all contribute to the long, slow disintegration of atomic structures. But they also leave open possibilities we do not yet fully understand. If protons decay via quantum fluctuations, then atoms are doomed. But if unknown quantum effects stabilize protons, atoms may persist far longer than current estimates predict. If vacuum fluctuations can trigger new forms of energy or structure, then what appears to be the end of atoms may simply be a transition into another state of matter that we have yet to discover. If quantum tunneling allows atoms to escape decay under certain conditions, then small pockets of matter could survive in ways we do not yet comprehend. The quantum world is full of paradoxes and surprises. While all current models predict that atoms will one day disappear, the deeper laws of physics may still hold secrets about how, or if, matter can truly be erased from existence. The journey does not end here. In the next section, we will explore an even greater mystery: the role of dark matter and dark energy, two of the most enigmatic forces in the universe, and how they could shape the final fate of atoms in ways we are only beginning to imagine. Atoms, as we understand them, seem bound by the strict laws of physics. They are the foundation of all known matter, and yet their fate is inextricably linked to the unpredictable, almost paradoxical rules of quantum mechanics. In the previous section, we explored how quantum uncertainty, virtual particles, and quantum tunneling influence the long-term existence of atoms. But the implications of quantum physics go even further. As we extend our reach into the distant future, deeper questions arise. Do atoms truly die, or do they transform in ways beyond our comprehension? Could quantum mechanics provide an escape route for matter, allowing it to persist in another form long after the classical universe fades into darkness? And if so, could the universe itself be reborn from the remnants of atomic collapse? These questions touch upon the deepest mysteries of quantum mechanics, bridging the line between science and speculation. When a proton decays, the atomic nucleus collapses, and the atom as a distinct entity ceases to exist. However, quantum mechanics suggests that information is never truly lost, a controversial idea with profound consequences. One of the most perplexing problems in theoretical physics is known as the black hole information paradox. In classical physics, anything that falls into a black hole is lost forever, crushed into oblivion. However, quantum theory suggests that information cannot be destroyed. Even if matter is obliterated, the information it carried must remain encoded in some way. If this principle applies to atoms, then their decay does not signify true erasure. It signifies a transformation into something else. But what form could this take? Quantum reformation in an infinite universe. If the universe exists forever, and quantum fluctuations occur at all scales, it is possible that given enough time, atomic structures may spontaneously reappear. This would not be a resurrection of specific atoms, but rather a reformation of atomic structure, randomly emerging from the vastness of quantum uncertainty. The implication? Matter in some form may be an inevitable product of an eternal universe. The role of entanglement in atomic persistence. Quantum entanglement is a bizarre phenomenon in which two particles remain instantaneously connected, regardless of distance. Some physicists speculate that entanglement may allow certain atomic properties to persist beyond decay, effectively saving information about atoms even after they cease to exist. This would mean that atoms do not simply vanish. Their quantum imprint lingers in ways we do not yet fully understand. False vacuum decay and the ultimate reset. Another mind-bending idea is that the vacuum of space itself may not be truly stable. If our universe exists in a false vacuum, a sufficiently large quantum fluctuation could trigger vacuum decay, rewriting the fundamental laws of physics and resetting the universe. If this were to happen, atoms as we know them would no longer exist. But new physics could emerge, giving rise to an entirely different kind of matter. In this scenario, atoms are not truly dying. They are simply temporary structures in a much larger, ever-evolving cosmic process. Most physicists agree that protons will eventually decay, meaning that atoms as we know them will one day vanish. However, what if there were an exception? Some speculative models suggest that exotic matter could form atoms that never decay. These hypothetical structures, if they exist, could endure even in the bleakest future. Extremely long-lived particles. Some particles, like neutrinos, are nearly massless and interact so weakly that they can pass through planets without being stopped. Could there be exotic particles capable of forming atomic-like structures that exist indefinitely? If so, then while normal atoms perish, a new form of stable matter could continue to exist in an otherwise dead universe. Black hole remnants as atomic successors. Even after atoms disappear, black holes will persist for far longer. If an exotic quantum process allows black holes to retain and redistribute atomic information, then they may serve as the final repositories of atomic history. These ideas are deeply speculative, but they highlight a crucial point. Atoms may fade, but their influence on the universe and its ultimate fate may persist long after they are gone. Quantum mechanics does not only govern atoms, it may also determine the final fate of the entire cosmos, a universe that never stops fluctuating. If quantum fluctuations continue indefinitely, then even a universe without atoms is not truly dead. Given enough time, particles, structures, and possibly even new universes could emerge from these fluctuations. This means that the end of atoms may simply be a transition into a state of infinite potentiality. Holographic reality. Are atoms just an illusion? Some physicists propose that reality itself is a hologram, meaning that atoms are not fundamental. They are merely projections of a deeper, two-dimensional structure. If this is true, then atoms never die because they were never truly real to begin with. They are simply the manifestation of underlying quantum information. This radical idea suggests that even when atoms decay, their quantum blueprint remains encoded in the structure of reality itself. As we dive deeper into the mystery of atomic fate, it becomes clear that their disappearance is not as simple as it seems. Quantum mechanics challenges everything we assume about permanence, decay, and even existence itself. Atoms may vanish, but their information persists. Atomic structure may collapse, but quantum entanglement may preserve echoes of what once was. The universe may reach a state of ultimate entropy, but quantum fluctuations could still breathe new forms of matter into existence. This leads us to an even bigger question, one that extends beyond atoms and into the darkest and most mysterious forces of the cosmos. How do dark matter and dark energy shape the final destiny of atoms and the universe itself? Atoms, as we understand them, make up everything we see: the planets, the stars, our own bodies. And yet, incredibly, they account for less than 5% of the universe. The vast majority of reality is composed of two mysterious forces: dark matter and dark energy. These unseen forces govern the structure of galaxies, dictate the expansion of the cosmos, and may even play a crucial role in the ultimate fate of atoms. But what if dark matter and dark energy are not just passive background forces? What if they actively shape the future of matter, determining when, how, or even if atoms will meet their end? Although it remains invisible and undetectable, except through its gravitational influence, dark matter holds galaxies together. Without it, the ordinary matter in the universe, the atoms that form stars, planets, and everything in between, would not be able to maintain their current structures. So what happens to atoms when dark matter itself begins to decay? Does dark matter decay? Current physics suggests that atoms will eventually decay, breaking down into fundamental particles like electrons, positrons, and neutrinos. But what about dark matter? If it also decays over long enough timescales, could it trigger a cascading effect that accelerates the breakdown of ordinary matter? Some models predict that if dark matter itself is unstable, then its eventual disintegration could create an energy imbalance in the cosmos, leading to unknown effects on atomic structures. Could dark matter prolong the life of atoms? Alternatively, if dark matter never decays, then it may act as a kind of cosmic scaffolding, allowing some structures to persist even after atoms themselves begin to fade. If dark matter remains gravitationally bound, it could influence decaying matter by slowing the rate at which protons decay, delaying the ultimate fate of atoms. This raises the mind-bending possibility that some atomic structures, perhaps those deeply embedded in dark matter halos, could persist far longer than previously predicted. Dark matter's potential connection to exotic atoms. If dark matter interacts with ordinary matter in ways we do not yet understand, could it stabilize certain atoms, preventing their decay entirely? Some speculative theories suggest that dark matter may form its own version of atomic structures, made up of yet undiscovered particles. If so, then even as ordinary atoms fade from existence, a new class of dark atoms may persist, completely invisible to us but playing a role in the next evolutionary phase of the universe. While dark matter holds galaxies together, dark energy is tearing the universe apart. It is the force responsible for the accelerating expansion of the cosmos, and as time progresses, this expansion will become more extreme. The expanding universe. What happens to atoms? The universe is not just expanding, it is accelerating outward at a rate that was once unimaginable. If dark energy continues to grow in influence, it could reach a stage where even atomic bonds themselves are stretched apart. This scenario, known as the Big Rip, would see atoms violently torn apart as the fabric of space-time expands faster than particles can hold together. The eventual isolation of atoms. Even if the Big Rip does not occur, dark energy will continue to expand space, isolating atoms from each other. In the distant future, even within galaxies, atomic structures may become so spread out that meaningful interactions become impossible. While atoms may still technically exist, they may be so dispersed that they can no longer form stars, planets, or any recognizable structures. The possible death of dark energy. Just as dark matter's fate is uncertain, so too is dark energy's. Some theories suggest that dark energy may not be a permanent feature of the universe. Instead, it could decrease over time, or even suddenly reverse, triggering a collapse of the universe known as the Big Crunch. If this happens, atoms might not decay into nothingness, but could instead be compressed back into ultra-dense states, potentially restarting the cycle of cosmic evolution. The interaction between dark matter, dark energy, and ordinary atoms is one of the biggest mysteries in physics. If we assume that all protons will eventually decay, atoms as we know them will inevitably vanish. However, if dark matter influences atomic structure or dark energy changes its behavior, the final fate of atoms may be far stranger than we currently predict. If dark matter remains stable, could it preserve remnants of ordinary matter long after atomic decay? If dark energy fades or reverses, could it trigger a new phase of matter formation? Could atoms transition into an entirely different form of matter, one governed by unknown physics? The end of the universe is often described as cold, empty, and lifeless. But if dark matter and dark energy are still active forces, the final state of reality may be far more complex than mere nothingness. The universe, as vast as it is, remains a puzzle, one in which only a tiny fraction of reality is made up of atoms. We've explored how dark matter holds galaxies together and how dark energy forces them apart. But now we must ask a more unsettling question. How do these forces dictate the final fate of atoms? If dark matter and dark energy continue to shape the evolution of the cosmos, do they provide a hidden mechanism that either extends the lifespan of atoms beyond what physics predicts, or do they hasten atomic decay, forcing matter into an unfamiliar and alien state? The deeper we investigate, the more we find that dark matter and dark energy are not just passive cosmic spectators. They may be the ultimate architects of the end of matter itself. Dark matter interacts with the universe only through gravity, refusing to reveal itself in any other measurable way. But despite its ghostly nature, it is a vital stabilizing force in the cosmos. Could it also play a stabilizing role in the longevity of atoms? Could dark matter prevent the collapse of atoms? As protons and neutrons slowly decay, the last remnants of matter will be subatomic particles drifting endlessly through space. But what if dark matter subtly interacts with atomic structures, preventing them from decaying entirely? If dark matter has any kind of unknown stabilizing force, it could extend the lifespan of certain atomic structures, keeping pockets of matter intact long after the rest of the universe dissolves. Does dark matter store atomic information? Even if dark matter does not prevent atomic decay, could it somehow store the blueprints of atoms? If dark matter carries information in an unknown way, perhaps through a yet undiscovered fundamental force, it could mean that even after atoms decay, their quantum signatures are somehow preserved. This raises an unsettling idea. Could atoms be reconstructed in a future phase of the universe, long after they seemingly disappear? Could dark matter form an entirely new type of atom? If dark matter has its own set of undiscovered particles, could it form a new kind of dark atom that exists outside the known laws of physics? These dark atoms would be completely undetectable by our current instruments, yet could persist for untold trillions of years after the last proton has decayed. If true, then perhaps atoms as we understand them are not dying, but simply transitioning into a different, invisible form of matter. If dark matter plays any of these roles, then the fate of atoms is not as simple as their decay into subatomic nothingness. Instead, they may exist in some hidden form, waiting for a future beyond our current understanding. While dark matter appears to act as a cosmic glue, dark energy is the opposite. It is a force of separation, expansion, and destruction, and its power is growing. The expanding universe and the death of atoms. As dark energy continues to accelerate the expansion of the universe, galaxies will drift apart. Then atoms within galaxies will spread further and further away from each other. If dark energy continues unchecked, it could eventually reach a point where even atoms themselves are ripped apart at the subatomic level. This cataclysmic scenario is known as the Big Rip, where dark energy overcomes all other forces, including the fundamental bonds that hold atoms together. Could dark energy dissolve the quantum fields themselves? Atoms are not just tiny objects floating in space. They exist within quantum fields that define their properties. If dark energy continues to expand space, could it eventually disrupt these quantum fields, causing atoms to collapse or cease to function as coherent structures? Some theories suggest that an extreme future form of dark energy could literally erase atomic stability, making matter itself impossible to exist. The ultimate isolation of atoms in a dark universe. Even if dark energy does not destroy atoms outright, it will continue isolating them from one another until every remaining atomic structure is separated by distances too vast to ever interact. In this scenario, the last atoms of the universe would exist alone, cold, and drifting eternally through an empty, lightless void, with no energy left to interact or change. This is arguably a fate worse than destruction, a universe where atoms continue to exist but serve no purpose, cut off from everything else forever. Given these opposing forces, dark matter as a stabilizer and dark energy as a disruptor, which one ultimately dictates the fate of atoms? If dark matter dominates, could it allow atomic remnants to survive, forming strange dark structures in the distant future? If dark energy continues accelerating, will it lead to a state where even quantum fluctuations are no longer possible, rendering atomic existence meaningless? Or is there another force at play, something beyond dark matter and dark energy, that determines what happens to atoms in the final moments of the universe? These questions lead us to the next phase of our exploration. What will be the very last atom to exist? Could one final atomic structure outlive all others, persisting long after all else has faded? The idea of a last atom, a single lone survivor of cosmic decay, is a haunting one. It forces us to ask not only what happens to matter in the end, but whether existence itself has an ultimate conclusion, or if something new is waiting beyond the horizon of time. As we hurtle toward the distant future of the universe, the fate of atoms becomes a question of cosmic importance. Will there be a single last atom, an ultimate survivor, outlasting all others? If so, what type of atom would it be? And how long could it persist before finally succumbing to the relentless decay of the universe itself? This question takes us beyond the limits of conventional physics and into the realm of extreme timeframes, quantum anomalies, and speculative yet scientifically grounded possibilities. To understand which atom might be the last to exist, we must explore the nature of atomic decay over unimaginable timescales. Whether certain atomic structures are more resilient than others, the role of quantum mechanics in preserving atomic remnants, the possibility that an eternal atom could exist under exotic conditions. If there is a last atom, it will not simply be a random survivor. It will be a testament to the deep laws of physics that govern the universe. Atoms are not all created equal. Some elements are naturally more stable than others, and the longevity of an atom depends on multiple factors, including the half-life of its protons and the strength of its nuclear bonds. The most stable element, iron. Atoms like iron-56 are considered some of the most stable in the universe. Iron sits at the lowest energy state per nucleon, meaning that nuclear reactions involving iron do not release energy, but instead require energy to proceed. This is why stellar fusion ends with iron. Beyond this element, fusion is no longer self-sustaining, leading to supernovae and black hole formation. Could iron atoms be the last to decay? If the fate of atoms is governed purely by nuclear stability, then iron might be one of the final atoms to exist before proton decay ultimately erases it. However, this assumes that the laws of physics remain unchanged over time, which may not be the case as the universe evolves. Exotic atoms and their potential longevity. Certain exotic states of matter, such as strange quark matter, may form atoms that are immune to conventional decay. If quark gluon plasmas or other ultra-stable configurations exist, then these strange atoms could persist for trillions upon trillions of years, outlasting all conventional atomic structures. Could the last atom be an entirely different kind of matter, distinct from everything we know? These questions take us into timescales so vast that even stars and galaxies are long gone. But there's an even greater mystery. How does quantum mechanics affect the survival of the last atom? Even if atoms face inevitable decay due to proton instability, quantum mechanics introduces uncertainties and loopholes that might allow a single atom to persist indefinitely. Quantum fluctuations, the last atom's final lifeline. The quantum world is never truly empty. Even in the deepest vacuum of space, particles and energy flicker into existence, governed by the uncertainty principle. If the last atom exists in a region of space where quantum fluctuations remain active, could these fluctuations periodically reassemble the atom in some form? This is highly speculative, but it raises an unsettling idea. The last atom may never be truly dead. It could be reconstructed repeatedly by the restless energy of the quantum vacuum. The atomic tunneling phenomenon. Quantum tunneling allows particles to cross barriers that classical physics says they shouldn't be able to penetrate. If an atom's decay is subject to probabilistic quantum effects, could certain atoms tunnel into alternate, more stable states, effectively cheating death? Some physicists speculate that under extreme conditions, matter might not simply cease to exist. It could transition into a completely new quantum state, one that is resistant to decay. Even if atoms eventually decay, could there be an escape route that allows some form of atomic existence to continue? Black hole remnants and the last atom. As we've explored, black holes may be among the longest-lasting objects in the universe. Some theories propose that as black holes evaporate through Hawking radiation, they might release exotic particles that retain atomic properties in some way. Could the final vestige of atoms be locked inside the dying breath of a black hole, waiting for an unknown cosmic process to reassemble them? Parallel universes and quantum persistence. If the multiverse is real, could atoms continue existing in alternate dimensions? Some theories suggest that when particles disappear in quantum mechanics, they may not be destroyed but shifted into other quantum realities. If true, this would mean that atoms never truly die. They simply move to another layer of existence beyond our perception. Even if one last atom persists for longer than all others, there will eventually come a time when it, too, must face its fate. If proton decay is inevitable, then even the most stable atom will eventually fall apart into free-floating elementary particles. If dark energy reaches extreme levels, it may tear apart even the subatomic components of the last atom, reducing it to pure energy. If the universe experiences a new phase transition, then the last atom may transform into a new kind of exotic matter, persisting beyond our ability to recognize it. As we reach the final stages of the universe's evolution, we are forced to confront an even greater question. Does the disappearance of the last atom mean the end of existence itself? Or could there be something beyond the death of matter, a hidden mechanism that restarts the cycle of the universe, giving birth to new atoms, new physics, and new possibilities? In the next section, we will explore one of the most profound ideas in cosmology: the universe beyond the last atom, an exploration of whether existence itself can continue, even after the last atom fades into the void. As we descend further into the cosmic abyss, an unsettling question lingers. What if there is one last atom, drifting alone through the void, persisting longer than all others? This solitary survivor would be the ultimate relic of a bygone universe, a final monument to the age of matter before everything fades into pure nothingness. But what would such an atom look like? Could it truly be alone? Or would there be a hidden cosmic mechanism that allows it to endure indefinitely? If protons have a finite lifespan, as suggested by certain grand unified theories, then all atoms will eventually decay. But the rate of decay isn't necessarily the same across all atomic structures. Some atoms may persist for far longer than others due to their unique properties. A cosmic outlier, the atom that refuses to die. In an extreme scenario, one atom may decay at a much slower rate due to quantum fluctuations. If atomic decay is dictated by probability, there could be a tiny chance that one atom outlasts all others, existing for an unfathomable length of time. Neutrino-proof matter. One of the speculative ideas in physics suggests that certain types of particles may interact so weakly with the known universe that they resist normal decay mechanisms. If an atom were composed of such particles, it could persist in a state of near invincibility, resistant to entropy itself. Frozen in time, the coldest atom in the universe. As the universe cools, atomic motion slows to a near standstill. Could the last atom be frozen in such extreme conditions that it stops changing entirely, suspended in a timeless state? If so, the last atom would be a prisoner of the universe's final temperature, drifting endlessly as a quantum fossil of the past. But even if the last atom persists longer than all others, there will still come a time when it too must face the unavoidable march toward oblivion. When the last atom finally decays, does it leave behind any trace of its existence? The universe's last energy release. If proton decay occurs, the final atom will break down into a burst of fundamental particles, scattering into the cold remains of space. This could be the last detectable event in the universe. A single, tiny flicker of energy before everything falls silent forever. Quantum echoes, the last atom's imprint. Some theories suggest that information is never truly lost, meaning that even after the last atom disintegrates, a quantum imprint of its structure might remain encoded in space-time itself. Could this quantum echo provide the foundation for a future universe, waiting to be reborn from the remnants of the past? If the last atom fades, does that mean existence itself is over? Not necessarily. This brings us to the biggest question of all. Does something come after the last atom? At first glance, the death of the final atom might seem like the ultimate end. A universe devoid of atoms, devoid of all structure, movement, or meaning, paints a picture of complete and irreversible silence. But is that truly the end of existence? Or is it merely a transition into something new? The end of atoms does not necessarily mean the end of physics. If we step back and examine the fundamental forces that shape the universe, we begin to see glimmers of possibility, hints that even in the face of absolute nothingness, reality may find a way to continue. Quantum rebirth. Could empty space spawn new atoms? The quantum vacuum is never truly empty. Even when the last atom decays, random fluctuations could still generate new particles. If these fluctuations persist, could new atomic structures slowly emerge over incomprehensible timescales? If so, then the death of atoms is not an end. It is the beginning of a new phase of cosmic evolution. The Big Bounce. Could the universe reset itself? Some cosmologists propose that our universe is cyclic. It expands, reaches a maximum limit, and then collapses, triggering a new Big Bang. If this is true, then the last atom is simply the final piece of an old universe before a new one begins. Could the remnants of atomic decay become the building blocks of a future reality, reforming into a new cosmos over incomprehensible timescales? If the universe is destined for an eternal dark era, what remains? Could there still be one final mechanism that allows existence to continue? Black hole information. Paradox. Is matter never truly lost? If information is never destroyed, could the history of all atoms still be imprinted in the fabric of reality itself? Some physicists believe that even when atoms decay, their information may be preserved in subtle ways we do not yet understand. This suggests that the death of atoms may be an illusion. While they vanish from our view, their influence persists in ways we cannot yet comprehend. A universe without matter. Could energy take over? If atoms eventually decay into pure energy, could that energy form the basis of an entirely new kind of existence? The laws of physics are built around interactions. If there is nothing left to interact, does that mean reality itself disappears? Or could the last remnants of energy reshape themselves into a new fundamental structure, one that replaces atoms with something beyond our current understanding? We began this journey with a question: what happens when atoms die? The answers have taken us through the deepest mysteries of physics, from proton decay and dark energy to the quantum secrets that might preserve information beyond the death of matter. What we have learned is that the end of atoms is not necessarily the end of everything. Even as the last atom fades into the void, new possibilities may emerge. Mechanisms beyond our comprehension may come into play. The universe may not be a one-way road to darkness, but instead a cycle of destruction and rebirth, waiting for its next chapter to begin. And if that is true, then perhaps atoms are not truly doomed. Perhaps in some unimaginable future, they will return. Perhaps somewhere out there, the first atom of the next universe is waiting to be born. Thank you for joining us on this extraordinary journey through the cosmos, here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.